Okay, so I will speak about two recent papers. The first is called Targets and Alls, and mostly we speak about it. And if there's some time left, I will speak about another paper. Okay, this is my co-authors, which is called Extreme Value Theory for Observations. Okay, so let's start with the first one. Okay, the work was motivated by the following reason. Suppose you have a dynamical system and you want to study the recurrence in rare sets. For instance, trying to do extreme value theory for these rare events. We think the idea was suppose in the phase space, in the ambient space where the dynamics evolve.
Sandro, sorry to interrupt.
Yes.
Gary was asking if you could make the slides full screen.
Okay.
That's okay.
Let me see if I could do it. Just a moment. Where is this? Wait. I should be able to do it. No, this is even worse.
People are saying Control H or Control L.
No, Control. No, usually it's simple, but I don't understand why I don't see it now. Okay, wait a moment. Control, you say Control?
Control L, probably.
Okay, good. It's okay now?
Not quite. Oh, yeah, here, perfect. Yeah.
Okay, it's okay. Okay, so okay, the idea is the following. Suppose you have we have a point which move in the phase space. Usually, if we want to study a recurrence of this point, you look at the distribution of the visit of this point in rare sets. But now we ask ourselves what happens if you have a set in the phase space, which we call the all, where if the point enters this set, it disappears. So basically, the idea was to study the distribution of the visit, of the first visit of a point into a rare set. A rare set means a set which is small and which becomes small when the terms evolve. But at the same time, the point should avoid a all which is placed in the phase space. Of course, the first question, okay, here on the slide, you see a few motivation, which we put in the introduction of the paper. Of course, the idea was to interest people in climate and now in the epidemiology, but okay, our study was basically just a prototype study with a very simple maps, as you will see in a moment. Okay, of course, the first question is, can we generate a dynamics for which at least something is left if we put a all which absorb all the points which move in the phase space. Okay, you will see that this is possible. Okay, so let me first of all give you. Okay, so all this situation can be described in the framework of extreme value theory. Namely, the question which we ask is the following: suppose we have this small set which I call a rare set, which is placed somewhere in the phase space. What the extreme value theory study is the distribution of the first visit of the point into this set. And at the same time, as I said before, we put some all. If the point moving in the phase space enter this all, it will disappear. As I said before, we have to guarantee that there is still a surviving set of points which we never hit the all when the time evolves. And of course, the target set, which is the rare set, for which we want to study the distribution of the first entrance, should be placed on this surviving set, because otherwise, if it is in the all, it disappears and nothing as there's nothing interesting to study. Okay, this is the situation. So for instance, you see here the target set, which is the rare set for which we want to study the distribution of the first visit. And at the same time, so there is the all. But there are 2 points, X. The first one, the orbit enters the all and disappear, but the red orbit is able to hit the target without entering the all. The question is, how many of these red orbits we could construct, and can we do the statistics of this orbit, namely the distribution of the orbit which enters the target for the first time? This is the question. Okay, first of all, let me give you the system. What is the maps which makes the point evolve in the phase space? Okay, so we consider, of course, it's a prototype example. So we started with very easy elementary maps, very easy elementary phase space. The phase space basically is the interval 0, 1, and we took maps of the interval of very particular kind, namely the interval is partitioned into sets. On each of these sets there is a map which is a smooth derivative larger than 1, and which is locally injective, but not necessarily onto the interval. Okay, we call this map Lasotto-York maps. And okay, there is a picture here. This is the map. So on each branch is not necessarily onto, but what is important in order to give rigorous result, at least in this framework, the derivative must be larger than 1 everywhere, plus other conditions which are usually satisfied for this kind of map. Okay, in order to study the statistical property of this map, and in order to build all the theory which I'm going to explain, it is important to introduce an operator which basically evolves measures, which is called the transfer operator, and to define a good functional space where this operator acts. And the space which we consider is the space of bounded variation. And the action of the operator is written here as usual. It acts on function of bounded variation, just summing the function on the preimages of a point x, provided we multiply it by what we call the potential g. Okay, now I will give you a particular form of this potential, which is suited to study easily the system. I will give you in a moment. This operator has a companion, which is its dual, which acts on measures, and the action of the dual of the operator on the measure is given by this equation. Okay, there is this factor here, which is a factor which is related to the choice of the potential. Okay, now I put this for completeness, but I will give you in a moment a more easy representation of this operator, which a better representation for the potential. In fact, it is written here, what we choose is the usual potential, which is 1 over the absolute value of the derivative. Because in this case, if we come back to this equation, the eigenfunction of the dual, which is a measure, which is exactly the Lebesgue measure, with the choice of the operator given by 1 over the derivative, this measure mu g is exactly the Lebesgue measure, which is the measure which is suited for instance, for numerical application in general. Okay. Okay, so this is the setting of the map. Okay, a very easy map of the interval, piecewise continuous map with a derivative larger than 1, which makes the map expanding. And we consider it a conformal measure. We can consider it as the ambient measure on the phase space, which is Lebesgue, which is just the eigenfunction of the dual of the operator, which I gave you before. And then we consider a hole, H, which is placed on the phase space. I will explain later on why this hole must be chosen very small. because we wanted to use some perturbation theorem which requires the all to be particularly small, but I will come back to its point later on. Okay, if I call x naught the complement of the all, of course, this is the set of points which are not in the all at the beginning. And if we want to consider all the points which will never hit or will never get into the all, we have to construct this set. So we have to take the preimage of any order of the all, and then we send n to infinity, and at the end we came with the set of points x infinity, which are the points which never enter the all during the iterations in the future. And this set is called the surviving set. Now, one question could be, is the surviving set, there are points in the surviving set, and what kind of set at the end it's left. Okay, so of course, there are very easy answer to this question. For instance, if we consider, we can have, for instance, periodic points. If the all doesn't contain periodic points, of course, these periodic points will never hit the all. So the surviving set can be made by some elementary class of sets, for instance, periodic points, if they are not in the all. But there are other conditions which makes the surviving set interesting from the geometrical point of view. In particular, if we take the map of the kind which I showed you before, and provided the all is sufficiently small, by the perturbation theorem which I evocated before, as a consequence, one has that this surviving set still is interesting and carries very interesting measures. I will show you in a moment what are these kind of results. Okay, one of the most important object which we are going to consider is what we call conditional invariant probability, which I'm going to define. Why is important for us? Because in a few minutes I will define. I have to construct a probability in order to study the distribution of the orbits. And this probability will be constructed using this measure, which I'm going to define, which is the conditional invariant probability measure. It is defined in a very natural way. Since we have an all in the phase space, on the interval in our case, we cannot define an invariant measure as usual. So we define something reminiscent of the invariant measure, but having in mind that we have points which are going to disappear. So if we take, for instance, if we have an invariant measure as usual, the measure satisfies nu time minus na equal nu a. Here we cannot have this because the points could get into the all. So we have to condition this to the surviving set at stage n. So basically, when we take the iterative order n, I have to condition to the set of points which are not, which are still in the interval and not enter the all, and this gives rise to this definition of conditional invariant probability. Since we are going to define some probability on the phase space in order to study the distribution of points, we would like to have this measure absolutely continuous in order to make, for instance, numerical simulations. So the question is, can we construct this kind of measures which are absolutely continuous with respect to Lebesgue? Okay, first of all, if we think a bit to the definition of this measure, you will see immediately that this measure cannot be supported on the well interval, but only on the complement of the all, so namely on the set x naught. And on this set is a probability measure. Moreover, it verifies the condition which is here. So if we take the measure of the surviving set at stage n, it decays exponentially fast with this number alpha, which is related to what people called the escape rate. I will come back to this definition at the end of this first part. Okay, now before defining the problem in terms of extreme value theory, I need still some technical facts and some technical definition. Okay, I introduced before the transfer operator, perturbation operator L. Now I have to introduce the first perturbation of this operator. There will be a second one later on. And this first perturbation of the operator consists in applying the original operator to an observable f of bounded variation, provided it's multiplied by the characteristic function of the complement of the whole. So if we think the whole as a very small set, and actually it will be, this operator is actually a small perturbation. This new operator is a small perturbation of the world one, because when the whole is very small, basically the characteristic function of the complement of the whole is large. So this is the idea, and you will see in a moment that the whole this set is not will become later on larger and larger, because the whole will become smaller and smaller. Okay, so now there is some property of this conditional invariant probability measure, which I have to state in order to continue. I told you before that I need this conditional probability invariant measure to be absolutely continuous, and it will be the case if the density with respect to Lebesgue, M denotes the Lebesgue measure, will be the eigenfunction of the first perturbed operator, which I introduced just a few minutes ago. So, for instance, okay, this is the operator which I defined, the first perturbed operator. If this operator has an eigenfunction which is H naught with eigenvalue alpha, and this eigenfunction H naught, which is a density basically, will be the density of this conditional invariant probability measure. Okay, so we can have this measure absolutely continuous if we can solve this eigenfunction equation for the perturbed operator. And what is interesting now is the following. If we take the dual of this operator in the same way we took the dual of the usual transfer operator, and with the same eigenvalue, we solve this eigenfunction equation, now this eigenfunction will be a measure, actually. And this measure, if we multiply this measure by the density which constructed before for the perturbed operator, we get a new measure, lambda, which is supported on the surviving set and is invariant for the map. So you see what happens. So we have this system at the beginning with the all. Okay, the point could disappear in the whole, of course, but a few of them will stay in the interval. This point which stay on the interval will be sit on the surviving set, and the dynamics on this surviving set will be invariant with respect to this measure lambda. And this measure lambda is constructed just in this way, looking at the eigenfunction equation for the operator and its dual. It is interesting to observe, and it will be important for technical issue later on, that this measure mu naught, which is called conformal measure, satisfies the equation which is written here. Okay, this equation is important for technical reason because it allows us to go from the dynamics, which is here, to the properties of the operator. And is the basic equation which will allow us in a moment to write the problem of the extreme value problems for the maps in terms of the operators. And then we use the spectral properties of this operator. Okay, now this is the technical introduction. Okay, one more thing which is important. again, another technical fact. In order to apply the perturbation theory, which I advocated at least twice before, we need some condition on the iterates of the original operator Ln and of this first perturbed operator, which is L naught. Okay, this condition, which are called Lazotte-York inequalities for the two operators, will be useful in order to develop the spectral theory, which I'm going to explain in a few minutes. And okay, so for people working in this business, these are very natural conditions the operator should verify. It's important to notice that this constant key is strictly less than 1, and it will play a role in the choice of the size of the hole later on. And the operator L and this first perturbed operator should verify this kind of inequalities with the same choice of the parameter. This is still necessary if we want to perform an easy approach for the spectral technique, which I'm going to explain later on. Finally, the two operators should be close, and this is one of the reasons why the hole should be small, because in order to apply the perturbation technique, we need this difference in L1 norm to be very small. In particular, it is dominated by the size of the hole. For this reason, the hole should be small, but I will come later on this. Okay, so this is the technical preparation for the map and for the operator. And okay, still not time to introduce the extreme value approach. One more fact, one more fact is the following. Once we have these inequalities and once we have this operator are close to each other, we can have the following representation for both the operators, either L and L naught. This representation, which are called in this framework quasi-compactness of the operator, allow us to see the action of this operator in this very simple way. Okay, suppose you take a function v, which is in the space where the operator acts. In our case, it's the space of bounded variation. The operator acts on each function in this way. It projects the observable along the direction of h. I remember you, h is the eigenfunction of the operator, and this factor is this expectation of the observable, plus an operator q, which is with norm which goes exponentially fast to 0. And what is important, the spectral radius of this operator is strictly less than the spectral radius of the operator L, which in our case is 1. It's 1 because we choose the Lebesgue measure for L as the conformal measure. So in this case, the top eigenvalue of L is 1. Since the operator L naught is close to L, as I said before, it enjoys the same spectral decomposition of the operator L, namely this one, of course, with a different density, H naught, and with a different eigenvalue, lambda naught, and the spectral radius in particular of this operator Q naught will be strictly less than lambda naught, which is strictly less than 1. Okay. So so the perturbation theory, which I'm going to use, requires that the original operator L and the perturbed operator L naught verify all this assumption, and this is true if we take the hole sufficiently small in such a way. Okay, this is explained in the first sentence. We need the distance between the L1 distance between the two operators so small, and this is dominated by the size of the hole, in order to get what is written in this first sentence. So basically, let's keeping in mind, the hole should be small. Why it should be small? Because if it is small, we have this representation for the operators. And in order to get it, we have to choose the size so small in order to get this what is written here technically. Basically, the closeness of the two top eigenvalue for the two operator Ln and not. Okay, now finally let's go to the statement of the problem. Okay, so as I said before, I fixed a point on the surviving set, which I called Z, and now I consider the following observable. I take minus the logarithm of the distance of a point x on the interval with respect to the target point Z. And then I look at the following observable, which is the maximum of phi of x of phi computed along the orbit of the point. So you take a point x, you compute the distance minus the logarithm, sorry, of the distance between the ethers of the point with respect to the target point, and you look at the maximum of this sequence of distances modulated by the logarithm. So it's very simple to get a geometric interpretation of this observable as is written here. So if we write the set which I'm showing here, namely the point where phi is smaller than u and phi composed with t minus n is smaller than u, you immediately realize that these are points which are in the complement of the whole at the beginning, stay still in the complement of the whole when they are iterated n minus 1 time, and eventually they jump into the ball B at after when the time is larger or equal to n. So B denotes a ball of radius e minus u around the point Z, and the set En, the event En, is nothing but the points which are in the complement of the ball, stay outside this ball for n minus 1 time, and eventually jump into the hole after n time. Okay, now I'm looking not at the hole, but I'm looking to the target set. I will introduce the hole later on. Okay, so for the moment, I'm introducing this observable. This observable concerned with the target set. And the target set is this one, is a ball around a point Z. The point Z is on the surviving set. So it makes sense for a point during the orbit to jump into this set, because this set is constructed around a point which is forever on the invariant set, on the surviving invariant set. Okay, so this is usually the observable which people introduce when they want to study the distribution of the first entrance into the target set, which is this ball. Now, as I said at the beginning, we could have points moving with t, which before jumping into this target set could fall into the hole. So we have to take into account. Okay, in this case, we have to take the following. We have considered a new events, which is given by En, which is this set, so the set of points which are outside the target set for n step and eventually go into the target set after n step. But this point, I want to be on at least for n times on the surviving set in order to be able to join the target set. Okay, so if I want the point, if I want at this point join the target set, they must be during the first n iteration on the surviving set, at least for the first n-1 step. Okay, so the question is now, can we weight this point with some probability measure? Because the idea now is to look at the distribution of the observable, of this maximum. But in order to study the distribution of this maximum, we need some probability which take into account the fact that the points which we want to target are still on the surviving set, at least for n step. Okay, and now this is the one. I'm not saying is the only one, but surely this probability measure allow us to do the computation. So I define this new sequence of probability in this way. For any Borel set on the interval and any n, I take the absolutely continuous conditional probability measure, which we constructed at the beginning, which is a measure which is absolutely continuous, so it can be used numerically if one wants to do some numerical application of this theory. And I computed it. Okay, I intersect. I take any set A, I intersect with the surviving set, and now I normalize with the measure of the surviving set at the stage n. This gives us a sequence of probability measure on the Wall interval. Okay, now if you look, okay, now let's come back for the moment to this observable. I want to study the the probability of this set. In particular, I want to study the probability of this event, which is nothing but the distribution of this observable. So I repeat, I want to apply a probability, which I'm going to construct, to study the distribution of Mn, namely the probability of these events, Mn less or equal to U. Okay, if we introduce the measure which is given here, it is straightforward to check that this probability gives us the following formula for the distribution of the events Mn less or equal to Un. Okay, for the moment, Un is, let's think Un as a parameter. I will see in a moment why I put the index n. Okay, so for the moment, this equation here is true even if Un, it doesn't depend on n. It's just a real number U, a positive real number U. Okay. Okay. If you apply these measures, this probability measure to this event, you see immediately that gives you this integral. So it's straightforward to check it, because if you remember, this An is nothing but a product of sets. And so if we write in terms of characteristic function, you get immediately to the definition. Okay, now the question is, can we get when n goes to infinity, because the idea is now to look what happens when n goes to infinity, can we get, look here, I want to get now the statistics of this object, namely to look what happens when n goes to infinity. Can we get some limit for this distribution when n goes to infinity? Of course, if you think a bit, if this U doesn't depend on n, it's very simple to show that this asymptotic distribution are degenerate. Namely, in order to get some result which makes sense, we have to normalize this boundary level U with n in such a way to get, in the limit when n goes to infinity, some non-degenerate distribution for this event. What is interesting is the kind of normalization, the kind of condition we have to set on UN in order to get a non-degenerate distribution in the limit of big N will be given directly by the spectral technique, which I'm going to explain in a moment. So for the moment, we only requires this UN depending on N in such a way we want to get a non-degenerate distribution in the limit. This is the only prescription which we give in a moment. I will show you in a moment that the prescription will be exactly this one, namely the measure of this ball, which is a target set, when the measure is the invariant measure taking on a surviving set, which I called before lambda, multiplied by n, should converge to some numbers. It must converge to some number. If it does so, okay, this is the good normalization in order to get a non-degenerate distribution for this probability. Okay, this is what we want to study. Now, this integral here can be in turn rewritten in terms of a new operator, which is the second perturbative operator, which I'm going to introduce. Okay, if you remember, the first perturbative operator, which is a naught, was obtained just multiplying the function v by the characteristic function of the complement of the target set. Now, I'm sorry, of the target, yes, of the target set. Now I take it and I multiply also by x naught. So this is the second perturbative operator. Okay, if we use the second perturbed operator, it is straightforward to check that this distribution in terms of this L tilde new perturbed operator is given in this way. Okay, so I repeat, the first perturbed operator was constructed multiplying by the characteristic function of x naught. Now I multiply it by the characteristic function of the complementary of the target set, because since the target set which go to 0 when n goes to infinity, this complement will become larger and larger. So for this reason, even the second operator can be considered a perturbation of the original one, which is L. Okay, so all this to say that this distribution can be written in this way. And as you see, this is very interesting for us because now we could try to use the perturbation theory for these three operators, in particular for L tilde, which is what is going to interest us, in order to try to get the distribution of this object when n goes infinity. And this is exactly what we are going to do. Okay, so the situation now is the following. I want to study this object using some perturbation of L tilde, perturbation which will be performed on the original operator L, since this characteristic function, in particular this one, BCN, will become larger and larger. So at the end, when n goes to infinity, will become 1. Okay, so now let's continue and let us show how this perturbation theory works. Okay, first of all, I have to introduce this object, which is an object which will play a role in the following. This object here, which is called RKN, is, from a geometrical point of view, is the points which at the beginning are in the target set, because I remember UBN is a target set. Then this point get out from the target set for k time and come back at the k plus 1 time, normalized by the measure of the target set. So this set will play a role pretty soon. So basically, I repeat, I wrote it in red here. This is the conditional probability of all point, conditional probability on the target set, of course, of all the points which at the beginning are in target set, which jump outside it for k time and come back at the k plus 1 time. And we will assume that these numbers, when n goes to infinity, converge for a given k, which is not usually the case in general, but I will show you that in our case, it does. Okay, now in order to apply the spectral technique, which I advocated several times already, we should require that this second new operator is close to the first perturbed operator, which in turn is close to the original one. So here are a few conditions, a few facts, which ensure us that this is actually the case. In particular, I look at this operator. I'm sorry, this is important to notice that this operator is indexed with n because it's constructed just using the characteristic function of the complement of the whole, and the whole now will be chosen with radius which is e minus un. Okay, so now I choose this radius of the ball as a function of n. For this reason, I intersect this operator with n. And I will see you in a moment how the prescription which I give you here, which comes naturally when we look at the perturbation of this operator. But before doing this, we have to guarantee ourselves that this operator, the new perturbed operator, is close to the first perturbed operator, which is close to the first one. And this is the chain of inequality, which are very easy to establish, which tell us that this is actually the case. And if it is the case, again, we have a quasi-compactness representation for this second perturbed operator, which depends on n, which is given by these two equations. Again, this number lambda n are numbers which are close to the top eigenvalue of L naught, which is close to the top eigenvalues of L. Okay, this is the chain of inequality which we have, and the spectral radius of Qn are strictly then to the spectral radius of Q, which is still strictly smaller than the top eigenvalue of the first original transfer operator. Okay, all these are easy consequences of the fact that we choose the all very small, which implies in particular that three operators are close to each other. If it is not the case, okay, all the theory should be redone in another way. Okay, these are still technical facts which guarantee us that this operator are close, and in particular, they must also verify some other conditions, because for the perturbation theory, which I'm going to use, these two operators not only should be close to each other, but they should verify other technical conditions. For example, this is one of the conditions. Namely, if I take the average of the first perturbed operator, average over the conformal measure, this should be of the order of the measure of the invariant measure on the surviving set of the target set Bn. Okay, so basically these are technical conditions which are required by the perturbation theorem, and still one more time, if the operators are close, it's not difficult to prove that all this inequality follows in our setting. Okay, now I introduced it before this quantity, which I call arca n, which are the points which are at the beginning in the target set. Then they jump outside for n time and come back, k time and come back. Okay, this set of points, if you multiply by the multiplier alpha, which is the eigenfunction for the first perturbed operator L naught, these are related to this object here, and this object here is the object which is given by perturbation theorem, as I will show you in a moment. And this object is important because it will give us what people call the extrema index when we will establish the distribution, the asymptotic distribution of our observable, and proved it will give us the Gumball Law. In fact, it's written here, the extrema index, which will modulate the exponential convergence in the Gumball Law, is given in terms of this quantity here. And for people working in this field, this extrema index has some interest because it's related to what people call the clusterization of rare events. And we will see in a moment that in our case, this extrema index can be detected and is related to the escape rate in some situation when we put the target set not around any point but around periodic point. But I will state it at the end as a final results. Okay, now is a brief explication of this spectral technique, which I told you we are going to use, because if you look at the representation of this distribution in terms, is written here, in terms of the perturbed operator, you will see immediately that if we can get, if we can perturb the operator of L tilde in terms, if we can perturb this operator in terms of the original one, we could be able to relate the top eigenvalue of this operator to the eigenvalue of one of the perturbed operator, and so to get an expansion of this eigenvalue. And this is exactly what happens. If I call lambda n the eigenvalue of L tilde, it verifies this condition here, just applying the perturbation technique developed by Keller and Liverani, which in our case is true since we already established all the conditions which are required in order to this theory could work, which I stated before, even if I state quickly. Okay, the main point is the top eigenvalue of lambda n, which is of L tilde n, which is lambda n, can be obtained by this asymptotic bound equality, and you see here appearing theta, which is the extrema index which I introduced before, this one, and lambda n is defined. Wait a moment. I put lambda n is this quantity here, is exactly the measure which the invariant measure which lives on the surviving set of the target set. This is what I call lambda n. Okay, so let me go back to this perturbation theorem. So we have an expansion of the top eigenvalue for this operator given in this term here. And now the computation is extremely easy because how can we compute the distribution? Simply in this way. Okay, I use the quasi-compactness representation of this operator, namely this one. Let me remind you this representation here. Okay, if I take the n power of this operator, okay, since the operator verifies this equation, I will have the n power of this operator, of this number, I'm sorry, which is the top eigenvalue. This remains the same because it's just a projection along the direction hn. And then I have this operator to the power n, just because of this simple representation. So if we come back to computation, which are here, this distribution here can be written in this way. So the operator here is replaced by its top eigenvalue to the power n applied to hn, and hn was the eigenfunction of this L tilde n time, and this is the coefficient, the multiplier in the which multiply h in the one-dimensional direction corresponding to the top eigenvalue, plus this term here, which is dominated by this operator, which goes exponentially fast to 0 in NOR. Okay, now if we replace this the power of this eigenvalue with this asymptotic equality, we get this formula here, and you see immediately that okay, all this term either disappear. This one will disappear because the spectral radius of this operator Qn okay, kills lambda to the power n here. Is written by the way somewhere later on. What is left is this object here. Okay, these two quantity goes to 1 for some reason which are explained here, and what is left is this quantity here, which is the most important for us. And you will see immediately that if we want this quantity to give us some non-degenerate limit, we need that this product between n and delta n should go to some fixed number. I remind you that delta n is the measure living on the surviving set applied to the target set, which is a ball depending, which is a ball with a radius which depends on un, and un was exactly this boundary level. And this condition is exactly what I wrote here before, this one. Okay, so lambda bn in the previous formula was exactly this quantity here. If this quantity goes to some fixed number, so what we get here is a fixed number, and so this became a constant in the limit of large n, because all the other quantities either disappear or goes to 1, as it's explained here using what was done previously. So you see the choice of the radius of the ball, which is shrinking to 0, because what we are looking here are points which start somewhere and then after n step enter this ball, or avoiding the hole, of course, because this takes into account the fact that the points are avoiding the hole. This enters this ball, but this ball is also shrinking to 0 because this is what is prescribed by the theory, by the way. And in order to get this convergence when n goes to infinity, the speed with which this ball shrinks to 0, which is given by un, is given by this requirement, namely the product between n, which is the time, and the invariant measure on the surviving set of the ball should go to a constant. Okay, this will play a role in the next, in the second part of my talk if I have time, because thanks to it, the extreme value theory is used in order to detect some dimension stuff related to the invariant set. Anyway, let me finish first of all this part here. So now we have done, because okay, these are technical facts related to the fact that we can discard this quantity here, in the sense this goes to 1 and the other goes to 0. But at the end, what we get, the important fact is we get this formula here, which is the Gumball Law. So namely, we get if we weight with this set of probability our events, and less or equal to UN, provided UN is defined, as I said before, we get to this asymptotic result, which is called the Gumball Law. And in particular, this is not a pure exponential, because it's modulated by theta, which was the external index, which I introduced before. And now the question is, can we compute this theta and see what's going on? First of all, let me tell you that this result is not a stationary result. Namely, usually extreme value theory is established when the underlying probability P makes the process, I mean the observable computed along the dynamics, this is the process. If we have an invariant measure, for instance, this process, of course, is stationary in probability, in the probability sense, and extreme value theory can be applied even using not the spectral technique, but using other standard techniques. Now, with this kind of sequence of probability, our process is not anymore stationary. This is easy to understand because even the probability change with the time n. So, strictly speaking, we cannot apply the usual standard technique because that requires not always, but very often that requires stationarity. What is interesting with these spectral techniques, we can go beyond the stationarity because we never used it in the deduction of this formula here. Okay, now let me briefly argue what is theta. Okay, it can be proved the following. If we put the target set around a point which is not a periodic point, plus other conditions, or regularity condition, which I'm not going to explain here, but are not very important. If we put the target set around a point z which is non-periodic, what we get is theta equal to 1. Which is usually what people expect in general. If we put the target set around points which are not periodic, usually the external index is equal to 1. At least in the deterministic setting. In the random setting is different, but it's not random this now. And instead, if we put the target set around a point which is periodic and still sit on the surviving set, because we have to require it, then, okay, then this number theta is not anymore 1, but is related to the escape rate alpha. The escape rate actually, the escape rate is not alpha, is minus log alpha. The escape rate is eta, but still, okay, what we have is the external index is related to the escape rate. So it's interesting, this connection between the escape rate, which in some sense take into account the presence of the hole, with theta, which instead takes into account the presence of the target set. This is the connection which we establish between the target and the hole. Okay, so this is basically what I wanted to say. How much time I have left? If I could go to the second part, because
so
not very much.
Very close to finishing. Yeah, maybe 4
Okay,
minutes.
so I've not time. So can I say a few words about the second part? Just just a few words. No. Okay. No, the second part was motivated by a different issue. Namely, we consider a different observable, which was not the distance between a point and a target point, but between the image of the point and the image of the target point. So basically, we call it the extreme value for observable. And the reason is the following. if we study this observable, then the boundary level, which are this number here, which I introduced before, are related to the local dimensions of this are related of the local dimension of the observable f. Just a few words. The local dimension of the observable f are defined in this way. Okay, so this is the image measure. So basically, this quantity here is the measure mu of the preimage of this ball by the function f. They are called local dimension of image measures. Okay, it turns out that this quantity here are very well studied by there are some very nice result about this quantity here, which I'm going very briefly to show you. And with the extreme value theory, we can get this number here, because this number here are related to the UN, and we can numerically compute the UN. So for this reason, I want to present this result, because they are useful for the application. So namely, this number here, which are called local dimension of the image measure, are the content of a very useful theorem, which I discovered when I was thinking to this business, which I didn't know before, which is the Ant Collection Theorem. So basically, the Ant Collection Theorem tells us the following: if you have, so basically, if we take an observable from this space to Rm, and we compute the local dimension of this observable, okay, this number are given by this result. So they are the minimum between the dimension of the image space and gamma, which is the local dimension of the measure, not of the image of the measure, but of the measure. Okay, and it turns out that if we can use the extreme value theorem, we can detect this number here, and so in some sense we can compute the image of the measure. And what is interesting is this theorem here is done on a class of function f, which are called prevalent, and which is reminiscent of what people does in measure theory when we introduce the concept of almost everywhere. This almost everywhere is replaced by prevalent. And last thing, using this theory and of the prevalent function and the dimension of the measure, we could get at the end some connection with the embedding theorem in the sense of tokens. And in particular, using the Ant Collection Theorem, it was easy to get the dimension of some sequence, some time series, which asymptotically go to some attractors, without reconstructing the attractors, which is usually what embedding theory does. So the message is the following: if we use this Ant Collection theorem on prevalent function, we applied it and we try to compute the image of the measure with the extreme value theory, we can get the dimension or an estimation of dimension of the underlying attractor when we study time series. For instance, we applied it to a very known map, which is the Lorentz map, and we get exactly the dimension of the attractor using as a function f any given function. In particular, use just one of the coordinate function composed with the dynamics. So I think this is a nice approach. I mean, a nice application of extreme value theory to the image measure, just because it allows us to compute easily this dimension of the measure in the setting of Ant and Collection. Okay, so I stop here. I think I use my time. Thank you very much.